My name is Avishai Nuckenberg on Twitter. I work for Aleph VC. Aleph VC is a venture capital fund, a very unique venture capital fund. And one of the things that makes us very unique is that we're one of the only VCs that have pretty good and strong engineering in-house. And we built a lot of really cool stuff. If you want to talk to me about that later, then I'm going to be around. But actually, this talk is not about Aleph. This talk is about serverless. And more precisely, this talk is about how to actually get the benefits of serverless. We have to change our thinking from the systems we used to build before the cloud to new type of system. And in order to build those types of systems, we have to fully immerse ourselves in the cloud, so actually understand the cloud and rethink everything that we do. So let me start the story about telling you about something I built many, many years ago, about 5 years ago. So back in the time, I was working for a company named Fewbytes. That was a consulting company. And we needed kind of a UI for our clients to see, how much billing, how many hours we're going to bill them for. So the problem was we were working with a service, a cloud service called Harvest. They didn't have a proper UI for that, so we decided to build one on our own. Fortunately, they had an API. But we didn't want to host servers. Like, we knew how to do it because we were consulting about, amongst other things, operations. But we didn't want to host our own servers and take care of that, so we decided to build on AppEngine. Now, I want to remind you this was 5 years ago. This was a serverless application 5 years ago. It was written in Clojure because I like Clojure and I got the task, so why not? And over 3 years, this has cost us a whooping $0. Amazing. 0 outages, almost no maintenance, pretty awesome, right? So this was the basic architecture of that application. Pretty simple. Had database, in this case, a cloud database by Google, run on AppEngine, written in Clojure, which is JVM stack, and talking to the Harvest API. That's pretty easy, pretty cool. But you will notice something very interesting. The architecture looks a lot like a normal server application. So cool, it's running on AppEngine. We're not paying a lot of money, but essentially it's still the same architecture. There's nothing new here, really. So, yeah, we had no servers to maintain, which is awesome. The cost was extremely low, almost no maintenance, 0 outages. But this all happened because this specific application didn't have a lot of load. If we got a lot of load, then, yeah, this would have cost a lot of money, not $0 like in this case. Because it was still centralized and still traditional architecture. Not very interesting. So let me take you a year backwards. 2012. And in 2012, we built, as a community service, we built a service called Web Fonts, or the Fonts project. Essentially, the problem back then was there was a service by Google called Google Web Fonts that served web fonts to everyone, except they didn't have support for Hebrew, no Hebrew fonts. So we wanted to do something good for the community. We wanted to build a service that allows serving web fonts in Hebrew, so all of us in Israel can enjoy it. So we wrote our own service. It was written in Python, but we didn't want to have the maintenance overhead. We didn't want to deal with scale. Remember, this had to serve a few million clients in Israel and abroad that used Hebrew. So we decided to build it on serverless. And again, this is 2012, so 6 years ago. This is basically the website. It's still running today, by the way. It's still active, 6 years, and running, still running, no problems. Pretty good. So essentially, you had a list of fonts that you could choose from, and you can then take a bit of JavaScript or CSS code and embed it in your website, and everything will be served by us, and everything would be automatic. And this is the architecture that we built. So basically, you have a browser. The browser goes to AppEngine, to a server on AppEngine, gets a dynamically generated CSS, which is customized to your browser, and then the browser by itself, without talking to the server again, would go to S3, cloud storage, and get the font by itself. And the way that the font gets there is that the designer goes to a website which is hosted on DigitalOcean, and this website would store the font in S3. So the interesting thing about this architecture is that actually, the client doesn't go through the server more than once. Now, usually when you build server applications, the way you talk to a database or to a data store is from the server. You basically delegate communication. You do everything in band. And you talk to the server, and then the server on your behalf goes talk to MySQL or some other storage or whatever. It's very uncommon for clients to be talking to storage themselves, right? But why not? I mean, S3 uses HTTP. It's essentially a public service. And in this specific case, the entire service was public, so no real problem. So this was a major win, and this was the beginning of our true serverless journey. So essentially, we exploited the fact that the delivery engine was stateless. We didn't need to know anything except what browser you have, and maybe where in the world are you. That was awesome. This means we didn't need a database. All the formats will serve directly from CDN or S3, so awesome. We could do client-side caching, so we reduced the load tremendously. All resulted in a very low-cost, low-maintenance system that was also multi-cloud. We used Google, we used Amazon, we used DigitalOcean. We didn't actually care what was hosted where. Very flexible, and we could optimize it. But this all worked because it was a very specific use case, and this was essentially a public service. So we didn't need to do authentication, hold state, or any of that stuff, which was very great because that service is still not costing us any money, and it's running for 6 years and serving all of Israel, which is awesome. So turns out that serverless is not really a new concept. If you remember CGI, Common Gateway Interface, which we used in the 90s and the early 2000s, this has been running the entire internet, and essentially it's serverless. If we subscribe to Amir's definition from this morning, you give code, you get an API, and you get a URL. So it's the same with CGI, except that the API gateway is called Apache. That's basically the only difference. And we had all those problems that we had back then. We still have them in serverless today. Cold start, connection pooling, all that stuff. We had those problems in CGI. So the concept is not really new. But there is something that changed fundamentally and made all of our architectures very, very different and kind of stops us from gaining the benefits of serverless if we don't change the way we think. So let's go a quick run through the evolution of cloud architectures. So this is essentially how a lot of us build services on cloud today. We have a client, we have a load balancer, we have a couple of machines, EC2 instances, and then we have a database. MySQL installed on some server, or maybe Cassandra, whatever, doesn't matter. Still the same. Communication goes in band through all those components. The client talks to load balancer talks to server talks to database. This is all pretty straightforward, very controllable, very linear, yeah. But then we start exploiting the cloud. So we say something like, okay, managing databases, that's annoying, that's hard, we don't want to do it. So how about we get managed database, maybe RDS? So yeah, we gained a little bit, we don't need to manage the machine anymore, but we still have to tune MySQL and deal with generating, creating users and MySQL clients and all that stuff, and we still talk to it through a server, which is nice. We gained a little bit, not very exciting. But then we decide maybe we want to use a database where we don't actually have to care about how much RAM is on the node, or how much disk space is on the node when we provision a node, or how many nodes we have. Like, who wants to scale MySQL, right? So maybe we change to Dynamo. And then we start seeing something very interesting, because Dynamo speaks HTTPS. Dynamo doesn't speak this weird protocol that SQL uses. It speaks HTTPS, like the load balancer, and like your server, and like everything else. Which is interesting. We'll get back to that in a second. So now we have a PaaS, or a SaaS, depending on how you want to call it. And we don't have to deal with servers, at least in the database. So the next logical step would be to get rid of the servers everywhere. So yeah, we'll get a Lambda. We get Lambda to speak to Dynamo directly. But this talks HTTPS to this, and this talks HTTPS to that. And it's all running on the public internet, right? Because Dynamo essentially is a public service. You can access Dynamo from anywhere in the world if you have the right credentials. There's nothing private about Dynamo. So why not just let the client talk to it? Isn't that better? I mean, if it's all public HTTPS anyway, we can just give credentials to the browser or whatever client you're using and have that browser talk directly to Dynamo. And no longer in-band communication between this and the server and database. Now we have out-of-band communication directly from the client to the database, which actually saves a lot of resources, because let's think about streaming 1 megabyte file from a database or a data store. If you have the server in band, you have to hold the Lambda or the thread or whatever it is that's running. You have to hold it open for the entire duration while you're sending data to the client. Why not have S3 or Dynamo deal with this, send directly to the client, and you don't have to pay the cost of being in the middle and serving as a router. That's actually much, much better. So we kind of moved to that kind of architecture, and the cloud supports it very, very nicely. For example, we have the Cognito service by AWS and equivalent services in other clouds, where you can generate tokens, you can generate credentials for each client very, very easily by using an API, and then all you have to do from your Lambda is go to Cognito and say, okay, I need credentials, and you can even give a token to the client or have the client authenticate independently with Cognito, get credentials, and from that point, it can just talk to all the services directly, SQS, Dynamo, S3, whatever you want, even complex services like machine learning and so on. It doesn't need the server anymore, and this is true serverless because we don't even talk to Lambda. The clients are doing everything by themselves. We only need Lambda to bootstrap this. So in a serverless world, we find something very interesting. If there are no servers, maybe there aren't any clients either. This is an architecture which is more like peer-to-peer than it is like the server-client architecture of before. Everything is essentially using HTTPS in the cloud, okay? Yes, even VPC. VPC is not a private network. VPC is essentially encrypted packets going over a public network because the Amazon network is public. Anyone can run services inside of Amazon. So yeah, VPC, encrypted packets over a public network, it's equivalent to HTTPS, which is also inherently encrypted packets over a public network. So, okay, if we don't need VPC, if it's the same as HTTPS, we can just run everything on the public network and we don't care anymore. And then everything can talk to database, to queue services, to whatever that we need, as long as they have the right credentials. And if we need to connect clients that we don't know where they are, or nodes that we don't know where they are, there's an easy way to do that, and the way is we use cloud messaging. Cloud messaging is sort of a bridge, I'll talk about that in a bit, that allows you to connect all of our infrastructure, all of our topology very, very easily. And the code can run anywhere. It can run in a browser, it can run on different services, it can run on different clouds. That's very, very interesting. So what we get something like that. We get this crazy topology where we have a bunch of nodes just talking to each other. Those nodes might be browsers, they might be a mobile phone, they might be a function running on Amazon, they might be a function running on Azure, there might be a function running on Google. It doesn't matter anymore. They just talk to each other over the public internet using HTTPS, and it's all fine. But this topology is also very adaptive, because this topology, this is maybe a snapshot of it, it can change by the minute, because we don't use service discovery anymore. So back in the day, we used a very static topology. I need to talk to this server, I go to DNS, or I go to console, I ask, where's that service? I get an address, and from that point, I start talking to that service, and I keep talking to that service all the time. That's great. I get a request, I do something asynchronously, I send a response back to the same queue every time, right? But if we use REST, part of the principles of REST is that we give hyperlinks. On every request, we give a hyperlink. That hyperlink could be where to send the response back. So essentially, the topology changes with every request that I give. One time, this client gets a request from, let's say, some Lambda, returns the response here. Second time, returns the response directly to Dynamo, because this is the URL that he got. So why not? So we get a very dynamic and changing topology, which is, again, very, very different. So in this architecture, there are no clients, there are no servers, all we have are nodes. And nodes run code. And we have two types of nodes. We have anonymous nodes and well-known nodes, meaning nodes that have a static address, that are easy to find, and we use them to bootstrap the whole process. But we have also routing services that can allow us to basically convert an anonymous node into a well-known node. Those services are API Gateway, which gives you an address, a URL for an anonymous, some function, Or it can also be stuff like message buses. Think about SNS or SQS or whatever your preferred cloud messaging service is. Think about IoT, for example. The IoT hub is essentially this broker that allows you to treat any device on the world as a known node that you can send messages to. And any public API that you have in the world is essentially a SaaS you can use and integrate into that architecture. So Google Maps, why not? Hacker News, why not? Twilio, why not? Anything that you need, if it has an API and it's exposed on the internet, it's part of your software, which is really awesome. So we've got a bunch of nodes. We've got a bunch of software as a service services that interconnect. They connect to each other directly. They speak to each other directly. No longer do we have private networks. We no longer have this separation inside and out. It's all outside. It's all dynamic. Just interconnects, kind of a living infrastructure. We only pay for what we need and what we use. And because we only use what we need at that specific moment in time, we pay almost nothing. We are no longer routers. We no longer pass through our functions someone else's communication. We don't act as a middleware anymore. We don't act as proxies, as routers. All the communication that needs to go somewhere just goes directly to that place. So we don't pay the cost of transferring that data, processing it, deserializing it, and everything. So it's much cheaper. But in order to achieve that, everything has to use cryptographic signatures, cryptographic signing, has to be secure from the bottom up, has to be built into the platform, has to be built into the protocols. This is a very different type of security from what we're used to. You can't just put a firewall and hope that it will work, because everything, again, is going over the public internet. And of course, REST is a very important part of that, because we need hyperlinks in order to replace service discovery and allow for that adaptive and changing infrastructure. And a lot of the state is actually in flight. We send a state to a queue, that state goes to some node, that node processes it, send that state as another message to another queue or another messaging service, and so on, so on, so on. We don't want to store state in databases if we can avoid it. So we talked about the nodes, but what are the nodes? Where are the nodes? Turns out that the nodes are everywhere. They can be generic nodes that can run whatever code, stuff like Lambda, or it can be a very specific node that are integrated with software as a service. For example, DynamoDB functions or S3 functions, stuff that is triggered by something that happens in a data store. But actually, there are more types of nodes which are more interesting. Turns out that a lot of the services out there in the world today have the ability to run your code embedded inside of them. So Twilio is a good example. It's an IVR, it's a voice service that you can use, telephony service that can run functions. They can run code that manages the chat or whatever conversation that they have. You don't need to do it on Lambda, you can just do it on Twilio. You have stuff like Zapier, which is like if this and that, but they can run code. They can run JavaScript and Python. And you can embed code inside of that. You've got services like CRMs that can also run code. Salesforce have something called Apex, which is their own language that they invented. Zoho has something called Deluge. Same idea. You can run code in Salesforce and in Zoho. Why not? You can run code on CDN, like Cloudflare Workers or AWS Edge functions, and so on, so on, so on. There are a lot of services that can run code. And if you start thinking about this, you get an architecture where the code runs practically anywhere on the internet and just talks to one another. So, for example, in Aleph, we built something that looks sort of like this. This is an architecture where we have an extension, a Chrome extension that is doing something on the browser, and it talks to a bunch of stuff on the internet and talks to them directly. So it gets work from one Lambda that talks to SQS, takes a job from SQS. The response URL could be another queue, could also be S3, can also be some webhook on the internet. So the response goes somewhere. Actually, they don't know, they don't care, they only care about the format. Results might be saved directly to S3. Logs are saved directly to Elasticsearch. We don't go through a server, we just talk directly to Elasticsearch, because again, this is also something that speaks HTTPS, so why not? And of course, all of this is orchestrated, and we get credentials by signing in through the normal mechanisms. What's interesting about this architecture is that if you look at this for a second, and you see that all the lines are going from here outwards, this actually looks like this is the server. The client actually looks a lot like a server in its architecture. This is a client-driven architecture, whereas before everything was driven by the server. Here's another example of something that we're building. So we've got a bunch of code, and it's run in parts in different places. We've got a class running in Salesforce, doing something. We've got some code in JavaScript that's running on AWS. They communicate through webhooks and queues, and then maybe the code goes to Twilio. Some code runs there. Twilio talks directly to Elasticsearch to save BI, and so on, so on, so on. Everything talks to each other. And what's interesting about this architecture is that there are no clients here. No browsers, no clients, just a bunch of nodes talking to each other with webhooks. So again, very, very different concept. So let's talk a little bit about what this all means. This is an inherently distributed architecture. And if you've dealt with distributed architectures, the more distributed your architecture is, the harder it is to manage. We've seen the pictures of the horrible dependency graphs, the Death Star of Netflix and AWS. This is what you're going to get. And this means that you will have to do much more ops than before. Yes, you're not going to deal with Linux servers, thank God, but you're going to have a lot of very interesting problems when it comes to monitoring, to understanding what talks to what, tracing your transactions, and so on, so on, so on. You're going to have multiple stacks because you might be running on multiple clouds, multiple services, multiple companies. They might support different languages. So you might have a code base that is written partly in Apex, Go, JavaScript, Python, whatever that service can run, which is also a very interesting challenge. Everything is inherently async, and the topology changes all the time. So monitoring, that's a very interesting challenge. But even more so, architecturally speaking, this type of architecture is inherently inconsistent. In the CAP theorem, we have consistency, availability, and partition tolerance. Over the public internet, we have no choice but to be partition tolerant. And we need that architecture to be highly available. That means we have to completely give up on consistency. So again, very interesting. It changes a lot of the concept that we use to deal with servers. With servers, at least we have the option of doing transactions. With serverless, not so much. No longer do we have this option. What about security? So everything that we do in traditional IT security, no longer relevant. You can't put a firewall because everything is on the public internet, so yeah, you can forget about firewalls. All those nice services that monitor your server and look for anomalies, again, not relevant. You can throw them all out the window. They don't matter anymore. Everything is now about crypto. You have to understand crypto, you have to use crypto, and credential management is essential because if I have credentials to your AWS account, I can do anything that I want. I can open up the VPC, I can go into your Dynamo, get all of your data, and the thing to understand is that the management interface of Amazon and Google and Azure are public, and they will always be public. So even if you think that you're protected because you have VPC, that doesn't matter. It's one API call away. Everything in your system is one API call away. So yeah, everything changes. And of course, because it's all API driven, everything is code. So why bother with this? This is extremely flexible architecture, extremely fast to set up. You can build crazy things with it in a hackathon, really, because all the power of the internet is within your grasp. It's very adaptive, and it removes a lot of layers of complexity and maintenance. It's I'd say the ultimate abstraction that we have now in the internet, just HTTP, everything that talks HTTP. Everything is code, so all you need is an ID, which is amazing, and it's very, very cheap if you do it correctly. And of course, there's a problem. How do we make this resilient and manageable? That's a very, very big problem. You can't do it, but you need to listen to that guy. That guy is Mark Burgess. Used to be a physicist, kind of transitioned into computer science about 25 years ago. He wrote something called CFEngine, which none of you have heard about, but this is the precursor to Chef, Puppet, and all of the cloud configuration management. He literally invented all of this. So he invented something called promise theory, which is a mathematical way to model dependencies and those types of architecture on the cloud. Very interesting, highly recommended read. but I'm not going to talk about that because I've got like 2 minutes. Final thing before I finish, so a lot of the projects that I've shown you, especially the fonts project, was written by this great group here, the staff of Fewbytes, so just due credit. So thank you very much, and if you have any questions, now's a good time.
If the client becomes the server and initiates all of the calls from the client side, how do you secure that? How do you protect yourself from malicious usage?
So excellent question. Like I said, this changes all of the security mindset. You can no longer trust services like firewalls and to protect you. You need to build security into your service. So this means that if you are afraid of people talking to you, if it's not a public service, you have to put cryptographic protection on your service. This means either sign-in, API authentication, stuff like that. You have to use strong crypto everywhere. There's no other choice. Yes, you're still vulnerable to the denial of service attacks, but you're vulnerable to those in the server too. Thank God that you're running on public infrastructure that knows how to deal with denial of service attacks very well. So if someone tries to attack your Dynamo account, they're attacking Amazon. Good luck for them. Okay, thank you.